Newton's second law of motion. We will see the statement first. The rate of change of linear momentum of a body is directly proportional to the external force applied on the body, and this change takes place always in the direction of applied force. This is the statement of Newton's second law of motion. Okay. So according to this, the statement, it is said that the force is directly proportional to rate of change of momentum. Rate of change of momentum here. Okay. That means F is directly proportional to rate of change of momentum. Suppose for small time interval dt, the change in momentum is dp. So for time interval dt, change in momentum is dp. So dp upon dt will give us rate of change of momentum, and that is directly proportional to the force, or the force is directly proportional to the rate of change of momentum according to the Newton's second law of motion. Now we can see here this F is equal to K dp upon dt. Since we have removed the proportional sign, we'll keep here a proportionality constant, say K here. So F is equal to K dp upon dt. Now you will see here, already it is said to you the force is a vector quantity and the momentum is also a vector quantity. You can see like this. Okay. So wherever this will work, the rate of change of momentum will work in whatever direction, in that direction the force will be there. Or you can say simply, wherever the force is directed, in the same direction the rate of change of momentum will take place. Okay. Now we can see here F is equal to K and P. We know that the momentum is equal to product of mass and velocity. So we can write in this way, d dt, this is mv. In place of P, we can write mv, momentum. Since mass is a constant quantity, it will come out of differentiation, and this is dv upon dt. Now F is one more factor that you can see here. The force is working in the direction of change of velocity, or you can say the velocity will change wherever the force is directed. Okay. So force is equal to Km. Here we know that for SI unit, this proportionality constant K has one value. So we'll put 1 here. So simply it is m dv upon dt, and the rate of change of momentum is defined as acceleration. So in place of dv upon dt, we can write here the acceleration. So it is F is equal to ma. Now again we can say here, wherever the force is directed, the acceleration is work, or the acceleration will be working in the direction of the force. Okay. Now we will see for the 3-dimension motion. If we'll just see for the 3-dimension motion, we can write F as Fx plus Fy plus Fz. It is in 3 dimension. That means a component of force in x direction, in y direction, in z direction. And the similar way we can write for the acceleration. We'll write this as this also, this way, Fx I cap, that is also the same meaning as Fx vector, plus we can write this Fy j cap plus Fz k cap. Now you will see we can write the acceleration as axi cap, ayj cap, azk cap. That means the acceleration also we have resolved in x, y and z direction, because it is we are taking for the 3 dimension. So if we just say f is equal to, this is fx is equal to max, fy is equal to may, or we can say fz is equal to maz. So what you will see here, ultimately the force, the magnitude of the force is measured by the product of mass and acceleration. That means the product of mass and acceleration give us force. So the Newton's second law of motion give us measures of force. Consequences of second law of motion. We know that according to the second law of motion, the force is directly proportional to the rate of change of momentum, and we have derived the magnitude of force is given by mass into acceleration. If the net force is 0, if net force F is 0, in such situation A is also 0, because M cannot be 0. The product of two number M and A is 0, so obviously M will be not 0, so A must be 0. Here it is indicating that the net force is 0. That means if many forces are working on any of the object and the net force is 0, means the force is balanced. Whatever force is there, that may balance to each other. In such situation, you will find that the acceleration will not produce, the acceleration is 0. Ultimately, it is indicating the Newton's first law of motion, which states that if any external force is absent, in such situation the object will remain in its rest position or in uniform motion in a straight line. So we'll see here, this is the consequences of second law of motion. That means the second law of motion is ultimately it is saying if the force is imbalanced, if the applied force is imbalanced, then only the acceleration is produced. That means to produce acceleration or to make any change in any of the object, the state of rest or the state of motion, state of uniform motion, or in the change in direction, the imbalanced force required. If the forces are balanced, the force is balanced. In such situation, F is equal to 0. So A is also 0. That means the acceleration will not produce. That means no change in the velocity, no change in the direction, and no change in the state of rest. And that will be simply the Newton's first law of motion. To understand application of Newton's second law of motion, we need to understand a physical quantity that is called impulse. We will define impulse here. The force which acts on body for a short time are called impulsive force, and the total effect of the force is called impulse. It is a vector quantity and denoted by J. The definition is given here. That is, the effect of a short duration force is the impulse. So if we just apply here the effect of the force which is applied for short duration, this is applied for short duration. That means this effect only is called impulse. So the impulse is product of force and that short duration. So force is F and the duration is suppose dt, because it is short duration, so we are just representing this with the dt here. Impulse is represented with J, and because the impulse produced is also small effect will be there, because the time duration we have taken is a very small, so the small effect will be there. So this small effect we are representing with dj, otherwise we are representing this impulse as j. So the dj is equal to f dt, or you can say that f is equal to dj upon dt. That means what we have learned here, the force is equal to, the force equal to dj upon dt, that means change in impulse, change in impulse. Okay. Now one more thing that you can see here, already we have defined in the Newton's second law of motion that force is equal to rate of change of momentum, that means dp upon dt here. So we can say the force, just see this equation, as I am writing here equation 1 and this is as equation 2. You will find that the right hand side of this equation, these equations are equal, so the left hand side also would be equal. So what you will find here, that f, the left hand side you have seen it is equal, so the right hand side also will be equal. That means the dj upon dt must be equal to dp upon dt, or we can say that the impulse is what here, this impulse, that means dt, if you will cancel, it is the impulse, the short duration, this impulse is equal to dp, that means change in momentum, change in momentum. Okay. So what we can conclude here, we can conclude that the impulse of a force which is product of average force during impact and the time for which the impact lasts is measured by the total change in linear momentum. Look at here, total change in linear momentum produced during impact, and the direction of this impulse is given by the direction of force. Okay, so this is the quantity, the impulse, by which we can see the practical application of the Newton's second law of motion. Okay, one more thing that you can watch here, this f is equal to dj upon dt here, or simply what we are writing, the effect is equal to force multiplied by the short duration time. So what you can see now here, this is f is equal to, the force is equal to dp upon dt, and if you just write this p is the change in momentum. So change in momentum is what? This is m, and already we have written this because m cannot be changed here. So m is not changed for a body. So f is equal to m dv upon dt. That means this quantity which we have written already, f is equal to dp upon dt. In place of this we can write f equal to m dv upon dt, or if you see the initial velocity is u and the final velocity is v, so in such cases what you will find, f is equal to m v minus u upon t, or dt you can write, and this is equal to, this is equal to what? It is equal to, if you just write this way, f into dt, so this is equal to m v minus u, and it is equal to j here. That means once again you will find the impulse is equal to f into dt. dt, if you take this side, it will become m in the bracket v minus u, That means J impulse is equal to mass into change in velocity, and mass into change in velocity is change in momentum. That means the impulse is equal to change in momentum. Impulse momentum theorem. See the statement. A given change in linear momentum can be produced by applying a larger force for a smaller time or applying smaller force for larger time. This is called impulse momentum theorem. Means, for example, you can see that if we have to produce same effect, or you can say the impulse should be same, so that can be produced by force multiplied by time, a short time, or simply you can say time, because here we are just explaining about the short time, larger force, and the smaller force for the long time. So here you can see that suppose I am taking here force as a 12 Newton. This force is 12 Newton and the time taken is 2 seconds. What it is? The time taken is 2 seconds. So what effect will produce here? That effect or the impulse is produced, and that will be equal to 24 Newton per second. That is 24 Newton second. Okay. This way the impulse will produce here. Okay. Now you can see what I can do. I am just telling here taking 6 Newton force, suppose. That means the force has reduced 6 Newton force, and I have to produce the same effect. That means the same impulse. So what I will do, I will just multiply this with the 4 second. What I will multiply with the 4 second, and the resultant will be 6 fours, that is 24 Newton second. Okay. So what actually I am doing here, I have applied a large force for a small time and get the impulse. The same way, same impulse I will get by applying a small force for large time. So this is called what? Impulse momentum theorem. Now we will see the application of Newton's second law of motion. For this, we'll see an example here. A cricket player lower his hand while catching a cricket ball. A cricket player, what happened whenever a ball he is catching, that time the cricketer is lower his hand like this. Okay. So actually what happened in such cases, when he lower his hand, you can see the first case here. Here the fielder is catching the ball here, okay, and after t1 time the ball is coming with velocity u, as the bowler or the fielder is catching the ball here after t1 time, so the velocity will become 0. Okay. Now you can see the second case, when the bowler has lower or the cricketer has lower his hand. In such case the time is t2 and the initial velocity as it is u and the final velocity is 0. But obviously you can see here in both the cases the time taken here is t1 and here t2, and where you will find t2 is more than t1. That means it will take longer time in the second case when he is lowering his hand. That time he is just taking more time to catch it. Okay. And what happened? How the Newton's second law is applied here? As we know that the force is equal to the dj upon dt, that means the change in impulse upon the time. Okay. Or we can say simply, as we have learned about the impulse momentum theorem, we can say it is change in momentum upon time. So momentum has changed here. Suppose the ball is having mass m, and as you know that the final velocity is v and the initial velocity is u here. So you can see that the final velocity is 0 and the initial velocity is u here. That means m0 minus u, or you can say simply minus mu upon t1. Okay. Similar way, you can see that for the second case, f2 is equal to m here. This is also equal to 0 minus v. That means the momentum is same here, only the change in the time. Okay. So f1 is equal to minus mu upon t1 and f2 is equal to minus mu upon t2. Now as we know here, the t1 is lesser than t2, so obviously you can find that f1 should be more than f2. Okay, that means the force in this case, that means the cricketer has to apply more force here to stop the ball, and here he has to apply less force. Okay, because the time is longer, because as the impulse momentum said, the time is longer, so the force is reduced here, and here the time is less, so the force will be more. That means the cricketer will hurt badly if he is not lowering his hand. So that's why it is the practical application that you can see whenever the bowler or the cricketer catching the ball, he is lowering his hand just because of the less force he has to apply, or he will not get hurt. Another practical application is there of the Newton's second law of motion, that a person received more injury when he falls from a certain height on a cemented floor than on the thick sand. Why it is happened? Okay, so we can explain this phenomena also by the Newton's second law of motion, in which you can see that it is a cemented floor. If a person is coming from certain height and fall on the cemented floor, the time taken is t1, and because the cemented floor is very hard, it will not compressible, so the time taken will be less here, and he has to stop in the upper layer itself. Okay, that means the time taken is less here, t1. Okay, but if the person with the same speed, if he is falling on the sand, thick sand, so because it is compressible, so it will take more time, it will compress in like this. Okay, so you will find that the time taken is t2, and the t2 will be longer than t1. That means t2 will be more than t1. As obviously you have seen, rest of the things are equal, like the mass of that person is same for both the cases, and the initial velocity also will be same in both the cases. The final velocity will be same in both the cases. So what is varying here? The variation is in the time. In this case, he will take longer time to stop. In this case, he will take a smaller time to stop, and so that you will find in first case F1 will be more, that means the force will be more, and F2 will be less here. That means he will get hurt when he will fall to the cemented floor. The force will be large, and here he will get, means he will get not that much injury would be there. Okay, in case of the thick sand. Okay, so this is the practical application of Newton's second law of motion.